Okay, here's the quiz, which is just construct the exponential shape, because today we're going to be talking about exponential functions. So go ahead, construct the shape, and then come back and see if you've done it right. Pause the video if you're doing this on the video. Okay, you had plenty of time. Now let's go ahead and construct the shape, which is pretty straightforward. You draw a rectangle, you have some bounding lines here, and we're going to label this. But right now, we're just constructing it. So what's the rule for constructing the exponential graph? Well, the red dot is right here. The center of the lower edge. We're going to have a line here that we want to label, and a line here that we're going to want to label, and of course, we want to label all the boundary lines, but I haven't given you the location of the red dot, so you don't know what to do as far as labeling. And I haven't given you the size of the rectangle, although we're going to start with just a regular 4x4 rectangle. So now, if you had trouble with that, does that jog your memory? Does that give you a hint as to how to start? Because if so, I want you to go ahead and see if you can do a little bit more. Okay, now, having seen this jogged your memory. Now, what I did, let's just make sure we understand what I've done. I've drawn a rectangle, fairly good sized rectangle on the paper. Then I drew dotted lines through each of the four edges of the rectangle. And those dotted lines extend to the left and to the right of the rectangle. And then I've drawn, horizontal dotted lines extend to the left and right. The vertical dotted lines extend from above the rectangle to below the rectangle, and we're going to label those. And we're going to do the labels away from the rectangle so they don't interfere with whatever we're doing inside the rectangle. Okay, now, we then start with a vertical line through the red dot. Remember, the red dot is at the midpoint, halfway across the lower edge of the rectangle. The next thing we do is we sketch a dotted line halfway between the right edge and the vertical line through the red dot. Now that vertical line through the red dot is through the center. Okay, so the line I just constructed is halfway from the right edge to that center line. And then halfway from the left edge to the center line. And there we're done. Okay? At least with the vertical lines. Now we have to do horizontal lines. Well, for every one of the graphs that we've talked a lot about, we always do a line through the center. A horizontal line through the center. Okay? So there we have it, horizontal line. And I'm going to say that line is right through the center. That's halfway from the top to the bottom edge. Then halfway from that line to the bottom edge, we do a second line. And we notice that line is twice as close to the center line as the center line is to the top edge. Okay, then from that last line that we drew, we go again halfway to the lower edge. And there it is. And then one more. Halfway from the last line to the lower edge. Now, we mark a point on each of our vertical lines and on each of our edges. The way we do that is we start at the left edge on the lowest construction line. The construction lines are not the lines through the edges. They're the lines that we drew within the rectangle. Okay, first point that we're going to have is on the left edge on the lowest construction line, not on the lowest edge of the rectangle. We're going to see shortly here why that wouldn't make sense at all. Okay, then we move over one line and up one line so that we're on the leftmost construction line, the one just to the right of the left edge, and the second line up from the bottom. We were on the first line up from the bottom. When we move up one unit, we're on the second line and so forth. So we draw the point right there. And then we move over one line and up one line so that now we're on the third line above the left edge and on the second construction line, the third construction line above the left edge and the second construction line as we count from left. And that is the middle line, so right on the middle line. Okay, then we move over one, which puts us on the third vertical construction line, and up one, which puts us on the middle line, which is the fourth horizontal construction line. And then we move one line over, one line up, and that puts us at the upper right-hand corner. We sketch a nice smooth curve, the smoothest possible curve. The exponential shape is the smoothest possible shape in a sense that I can't really describe because it involves some more advanced mathematics for the description, but it's the smoothest possible shape. So draw the smoothest curve you can, and you're probably going to have very good exponential shape. All right. So here's the exponential shape. I'll even label that. And it's sketched within a rectangle. Rectangles often pretty much square. I've got this one a little wider than it is high, but that's a matter of taste. And you also want to adjust the shape of the rectangle for whatever it is you're trying to do with the function. But for right now, a square or a golden rectangle, whatever, is going to give you a fine shape. Okay. Now I want you to sketch a couple more lines. Okay. I want you to sketch the line halfway between the center, the vertical line through the center and the line to the right. Okay. So halfway between vertical center of the line just to the right, and then halfway between that line and the right edge. So sketch a couple of dotted lines halfway. Well, okay, you should do that, but I know you know how to do that because you did a good graph. So I'm going to draw the lines I mean. If that line is halfway, this line is halfway. I mark the point where each of these lines meets the graph. And then I draw a horizontal line through each point. And I'm going to extend those horizontal lines just a little bit. Now, I'm going to notice something. Every time I move over one and up one, I move over one and up one, I'm always doubling the value. Okay? Because take these lowest two lines. Okay? The second line up from the lower edge was used to construct the first line up from the lower edge, the one halfway between it and the lower edge. So if the lowest construction line is halfway between the lower edge and the next higher construction line, then every construction line is twice as far from the lower edge as the one before it, which means that the value of the function doubles. Every time we go over one vertical construction line, the function gets twice as big. So I'll say that the y values or the y value double every time we move over one construction line. Just to be complete, I'll say move over one vertical construction line. So if we move from here to here, the y value doubles. If the y coordinate here is half of the y coordinate here. The y coordinate here is half of the y coordinate here. So if we go from this point to this point, y doubles again. Y is this big and y is this big. Okay? And proceeding on to the right. Now I want to test between the two construction lines I just asked you to draw, halfway between the second and third construction line, halfway between that line and the right edge. If we move from one of those lines to the next, we move just as far as we do if we move from one construction line to the next. In other words, well, we're going to put numbers in this in a minute. The point I'm making then is that if this graph is truly an exponential graph, then this line, the construction line for the higher of the 2 points, is twice as far from the lower edge as the construction line through the first of the 2 points. Again, we're talking about the 2 points on the new lines. They aren't construction lines, but they're vertical lines that we've drawn. Now let's go ahead and do a little labeling. And if some people already labeled these, the left edge, people wanted to label x equals -2. I was going to use something different, but I'll go with your labeling. Then x equals -1, x equals 0. So on the left edge, the value of x is always -2. On the center, the value of x is always 0. Halfway between -2 and 0, we have a vertical line. That's x equals -1. And then the next vertical line over, next vertical construction line is at x equals 1. And then a line at x equals 2. So the two construction lines I ask you to draw are halfway between x equals 0 and x equals 1, halfway between x equals 1 and x equals 2. Well, that means that those lines, where is it? Had in my hand, x equals 1/2 on the construction line, halfway between the middle construction line and the one to its right. And then x equals 3/2 or 1.5 between the left edge and the construction line just to its left. So when we move over here, we move up a certain distance. We could draw a fundamental triangle for these 2 points, the 2 new points. What we really want to do, though, is see what we think our y coordinates are. Now, I believe at least one person labeled this, and the lowest line is y equals 4, the lowest edge. Am I right? Does that correspond with, okay. And did you use 8 for the high one? Show me with your fingers. Or I'll come back there and look. 16. Okay, that's good. So use 16 up here. So I'm labeling the dotted line through the lower edge as y equals 4. The dotted line through the upper edge is y equals 16. The dotted line through the middle is halfway between 4 and 16. A lot of ways to get halfway between 4 and 16. You could add 4 and 16 and divide by 2 and you get 10. Or you can say from 4 to 16, we go up 12 units. If we go up half that many, that's 6 units. Has 6 units above 4 is 10. And that's 6 units below 16. So we know that the center line would be y equals 10. Is that what you had? Okay. Okay. Then halfway between 4 and 10 is y equals 7. Just labeling the construction lines. Halfway between 4 and 7, now things get a little tricky here because our fractions get a little obnoxious, but this would be y equals 5.5. And the lowest construction line, which I'll label off to the right because things are getting crowded on. Well, no, actually, I'll go ahead. And I labeled that one X, it's Y. Okay. Now let's see, 4 and 5.5 is 9.5, and half of that is 4 3/4. Now I've tried to be nice to everybody and not use things that divide up into halves and quarters and stuff like that. But those things do occur, so we might as well get used to that idea. Okay, and remember, each of these values is calculated either by averaging the value the y value at the lower edge with the y value just above the line we're labeling. Okay, we average, well, kind of forget that statement, what I said earlier. All right. So now what I want you to do is estimate your y values for the 2 lines, for the 2 new points that we constructed, okay? For the point on the x equals 1/2 line and the point on the x equals 3/4 line, what do you think y equals? Okay, now everybody pretty much estimated that this should be y equals 8, which makes sense. Here's 7 and here's 10. It's closer to 7 than it is to 10. So 8 is probably about right. And then up here, here's 10 and here's 16. Halfway between 10 and 16 be 13. This is a little less than 13. So y equals 12 is a pretty good estimate. Now, down here, we have the line y equals 4. So that you show me your fingers, what's the length of this arrow? The arrow that goes from the y equals 4 line as a lower edge to the y equals 8 line, the one that we drew in to get 2 points. So how far is it from here to here? Yeah, obviously it's 4. Okay. And from here to here, how far is it? Down 1 finger. No, yeah, no, it's 8. At 9 fingers. Okay. Okay, so this is 4 units. This is 8 units. As it turns out, if you draw a good graph, if you put any 2 points on the graph where the x values are 1 unit apart, then that's the case. We have the x equals 1/2 and the x equals 3/2 line. Those are 1/2, 1 unit apart. Okay. And our distance from the bottom edge doubled from the x equals 1/2 point to the x equals 3/2 point. Okay. And it should be double. Just as the distance of each, if we start from the left edge and draw the construction points, each construction point is twice as far from the lower edge as the one before because of the way we constructed the graph. Halfway to the lower edge, then halfway to the lower edge, and so forth. So here's a property of the exponential function. I'm not gonna say this property in terms of this graph. I can do it, but I think it would be a little confusing. I'm going to draw a toolkit graph just real quickly. Okay, there's the grid. And here are the points. All I'm doing is the same thing I did before in a rectangle. It's a little smaller rectangle. But my y values, I'll use the standard values for an exponential function, or toolkit, the basic toolkit function, y equals 0 to y equals 4. And x equals 0, x equals 4. Okay, so you should construct one. Label the left edge x equals 0, the right edge x equals 4. The upper edge y equals 4, the lower edge y equals 0. We put a red dot at the intersection, halfway. Put a red dot at the midpoint of the lower edge. Then we can label our y values, which are 1/4, 1/2, 1, 2, and 4. Now, from the y equals 4 line down to the lower edge, if we go halfway, we'll be at y equals 2, right? And halfway from 2 down to the lower edge is at 0. Halfway from 2 to 0 is 1. Halfway from 1 to 0 is 1/2, and halfway from 1/2 to 0 is 1/4. So 1/4, 1/2, 1, 2, and 4 are the values. And every time we move over 1 unit, we double the y value. The y value at the leftmost point, the point on the left edge, is 1/4. The y value on the next vertical construction line, which in this case, I've got to back up. I said something wrong. I said we were going from x equals 0 to x equals 4, and our toolkit graph goes from x equals -2 to x equals 2. Let's go get the mass. So let's correct that. Left edge, the line is x equals -2. The right edge, the line is x equals 2. And then we have the line x equals 1, the line x equals 0. That's our x equals -1 and x equals 0. And x equals 1 and the x equals 2 line. So if we go from the x equals -2 line to the x equals -1 line, the value doubles. If we go from the x equals -1 to x equals 0, the value doubles. So we see that every time every move from one construction line to the next doubles the y value. And that's your toolkit exponential function. So for any exponential function, you construct it this way. We call the distance between vertical construction lines the doubling time. Now I can refine this a little bit. I'm going to stay with this. I say this is a doubling time in the sense that it doubles the distance from the lower edge. Sure, you can see the whole board. Okay, there's my statement. We see for the toolkit function, since the lower edge is at y equals 0, that amounts to just doubling the y value. Over here, we don't double the y value on the original graph because the lower edge is at y equals 4. Our distance to the two to the horizontal lines from the two new points that we put down here, the values of y equals 8 and 12, and that's not doubling. But the distance from y equals 4 is doubling. Distance from y equals 4 is 4, then it's 8. And just as between the x equals -1 and x equals 0 value on this original graph, the first graph that we drew, y goes from 5.5 to 7. That doesn't double. 5 and 7 is not the double of 5.5. But if we look at the distance from the y=4 line, the distance from 4 to 5.5 is 1.5. The distance from 4 to 7 is 3, and 3 is the double of 1.5. So our distance always doubles. And we can draw little arrows indicating those doublings. Okay. I'm going to draw little arrows that indicate our distance on the vertical construction lines from the lower edge. Each of these arrows is twice as long as the other one, which is just another way of saying what I've been saying, that the y value exceeds the y value at the lower edge by twice as much each time we move over one line. So that these lines are doubling times. Might be a little hard to read. I've got T with a subscript DOUB, T dub, okay? Time it takes to double. Now I'm saying time when we're using X, and X is not the variable we usually use for time. But in most applications of the exponential function, as we're going to see, not all applications, but in most applications that we run into, the horizontal coordinate will be time instead of X, like, okay? So we could use T just as well as we could use X. Anyhow, just to make the picture complete. Distance from the left edge of the first construction line is a doubling time. From that line to the next line is a doubling time. Okay, the distance between our vertical construction line is always a doubling time. And the doubling time is a big deal. That's the first thing I want you to see about the exponential function. You're going to see, I think, the rule of 72 in your textbook, in the open math videos, and so forth, okay? And the rule of 72 says, take the percent interest on an investment. Divide that into 72, and it tells you how long it's going to take it to double. It's very simple and very easy to get used to. Just remember 72. So I'm just stating this. It's not exact. It works better for some interest rates. If the interest rate gets too big, it doesn't work very well at all. The small interest rates, it works pretty well. Okay, so I'm going to sketch an investment. How much money do you want to invest here? Let's say, you probably haven't had time to earn a whole lot of money. Let's say you've only got $100,000 to invest. Okay, you want to see how long it's going to take that to grow to 200,000. Okay, well, obviously, most of us think in terms of lower numbers, but let's say we'll consider $100,000 at 4%. Well, I'm going to go ahead with our red dot at the center and draw our construction lines. And then we're going to go ahead and it wasn't a great graph. It's a little too straight down there. It's actually kind of got the wrong concavity there, but I'll blame that on the chalk. Okay, here's our graph. Now we haven't labeled it. We're going to label it for this investment. And we're going to say that x equals 0, except instead of x, we're going to use t. T equals 0 here. T equals 18 here. T equals 36 here. And I'd like to be sure that this is going to show up. Just to be sure I don't completely trust the camera. Okay, I'll put t equals 36 here. And then t equals 54. And t equals 72. All right. Now, from t equals 0 to t equals 18, the y value doubles. From 18 to 36, it doubles again, just like in the previous graphs. Is that clear? Does that make sense? Okay. Now, let's say we start at t equals 0. I don't want to write all those zeros instead of 100,000. I'll write 100K. Okay. Then you did a good job of labeling your y values for. So instead of y, I'm going to use p for principal. Okay. How much your money's worth, how much your account is worth. From the left edge to the first construction line, in other words, from t equals 0 to t equals 18, we go up to 200,000. Then between that vertical line and the next one, between t equals 36 and t equals 54, so sorry, let's say no, between t equals 18 and what am I looking at? Yeah, between t equals 18 and t equals 36, principal goes up to 400,000. Then between t equals 36 and t equals 54, it goes up to 800,000. And then between t equals 54 and t equals 72, doubles once again. It's 1,600,000 or 1.6 million. Okay. So if you're 20 years old right now and live to 92 and everything stays stable, you could see this kind of growth. Now that wouldn't necessarily be the actual growth in the value of your money because there's also inflation. But this gives you a picture of how the amount of money in an account at 4% would grow over, basically over a lifetime. That makes sense? Now, I usually use a lowercase, it's something between uppercase. Okay. Remember the y equals a f of x minus h plus k, which is what we've been using so far. A is our vertical stretch or compression or reflection factor. Horizontal shift is h. Vertical shift is k. If the width of our rectangle is 4, this applies. Okay? If it's other than 4, like, okay, here the width of the rectangle is 4. On the toolkit function, the width of the rectangle is 4. But in this case, the width of the rectangle is 72. Okay? You saw in the first chapter, you have a horizontal compression factor, the number in front of your x minus h. What you think of is you take your toolkit graph, you stretch, compress, stretch or compress depending on the value of a, and if a is negative, you reflect it. Then before you do your horizontal and vertical shift, if you've got some number in front of x, you have to horizontally compress it by that amount. So this C is your horizontal compression, stretch, or reflection. If it's negative, you got to flip the graph around, reflect it this way, turn it this way. So instead of going up, it's coming down. If you have a big horizontal compression factor, that compresses the scale of your x values or t values in this case. If that compression stretch reflection factor is less than 1, some fraction, that spreads it out. Here in this example, I didn't label it before, but the bottom line is still p equals 0. So from the basic toolkit graph, Can you tell me what the horizontal shift is? Well, on the base toolkit graph, the red dot is at the origin. It's at x equals 0 and y equals 0. Now it's at t equals 36, just like x equals 36. So the horizontal shift is 36. And the vertical shift is 0. Your horizontal compression stretch factor, you're going from a toolkit graph that's got a width of 4 to a graph that has a width of 72. So C equals 4 over 72. Your P values, like your Y values, go from 0 to 1600, whereas on a toolkit graph, they go from 0 to 4. So that A equals 72 over 4 equals 18. So the equation here, instead of x and y, we've got p and t. So your principal will be a times 2 to the c times x minus h plus k. Why is it 2 to the c times x minus h? Because your toolkit function is f of x equals 2 to the x. Okay. Now you might not remember that, so I'll write it down. It's y equals 2 to the x. So here's our principal function. Now we can put the numbers in. The numbers are A is 18. Uh-oh. What I wrote down for A is ridiculous, a vertical factor. I even said the right numbers, and then I wrote down the reciprocal of 4 over 72, which has nothing to do with the vertical. A is, and I pointed to it, your vertical goes from 0 to 1600, whereas the toolkit function is from 0 to 4. So you're stretching it by a factor of 1600 over 4. So when I write this out, this is then 400 need even more room. Multiplied by 2 raised to the C, which is 4 over 72, times the quantity T minus 36. Which is 400 times 2 to the 1/18 times T minus 36. Now, I'm assuming we understand the toolkit function. But just for reference, here it is. There's our toolkit function. If we replace X by T and Y by P, then let our T scale go from 0 to 72, and our Y scale, which is now our P scale, go from 0 to 1600. We get these shifts, stretches, and compression factors, okay? Now that all goes back to chapter 1 where we learned about transformations. So we're going to have to build that up. The point here then is that given any phenomenon that has a constant doubling time, another example might be the population of a herd of animals. You're starting a herd with a couple dozen animals, and you got 15 square miles of pasture. So they got all they want to eat, and they're going to reproduce. And after maybe 3 years, the population is doubled. And after another 3 years, it's doubled again. So pretty soon, in not that many years, you're going to have a whole 15 square miles of pasture with a herd of whatever you happen to be herding. Now, when they occupy that whole 15 square miles, then they're going to have to start competing for space and food, so they don't double as quickly. They don't have as much food to carry healthy young. They spend more time fighting, okay? Stuff like that. So that there's a limit to how long that exponential growth will go, but right there is your exponential growth curve, okay? And it has a constant doubling time. If doubling time is 3 years and you start with 120 animals, well, they're gonna have 40, 80, 160, 320 after 4 doubling times. Okay, that'd be 12 years in this case. Still gonna take a while to get up to huge numbers, but nothing interferes, he'll get there. Okay, well. It's often written A f of cx plus k, your general exponential function, in terms of your toolkit function f. This is another form that can give you the same results. One example, you have y equals a times 1.5 to the x. As you'll see, at some point, I'm going to make some graphs. Of y equals b to the x. If b equals 0, sorry, b equals 1, then b to the x is 1 to the x. 1 to any power is 1. So you just have y equals 1. If b equals 2, you get the function, the shape that we just drew. Okay? And when x equals 1, y equals 2. If b is 1.5, then when x equals 1, 1.5 to the first power is just 1.5. We're going to have an exponential function like this. Now, no matter what b is, b to the 0 power is 1. Remember, any number to the 0 power is 1. So every graph of a y equals b to the x goes through this point. Now, to get the graph of b equals of y equals 1.5, we have this point and this point. In order to draw a nice smooth curve, we have to start higher here and go up more gradually. So there's our b equals 1.5 graph. We could also have the b equals, well, we don't know. Yeah, the b equals 1/2 graph. That means when x is 1, 1/2 to the x would be just 1/2. So we go through this point and this point, and we have a graph that's a backward version of this graph. 1/2 to the -1 is 2. So the graph would have to go through these 3 points. It's going to look like this. Now, this graph and this graph are reflections of each other. So you're going to see graphs that look like this with maybe a few more curves, and you want to understand that. In the section that we're going to assign for homework, you'll have something like P equals 50 times e to the 0.07t. Okay. Tell you just a little bit about E. It's a button on your calculator. You got an E button on your calculator. And you can use it because you can't do the calculations. Okay, except for very simple values of x. If I go up to y equals 3 here, you have a point here and try to make an exponential function. Now this function's going to come down steeper. It's going to approach 0 faster. This is the b equals 3 function. I don't have room to write b equals 3, but this is y equals 3 to the x. So here I've got y equals 2 to the x. Here I've got y equals 3 to the x. E is a number that's a good bit closer to 3 than it is to 2. Here's our y equals 2 line, y equals 3 line. Here's the y equals e line. If I sketch this point and sketch the exponential function, that's coming out exactly where I want it. I get the function y equals e to the x. That's approximately where it is. Okay. E is approximately 2.7. It's actually 2.71828. And then there's another 1828. And you think it's going to repeat, but it never does. Okay. It just goes on forever. So for now, E is just a number you can punch into your calculator. So P is 50, e to the 0.07t. You can find P values for any T value and answer questions and get some idea of what exponential functions might be good for. So that's the assignment. you're gonna have for next time, so. Work on that and get your feet wet, and then we'll get into more details.